Good afternoon. It's a pleasure to be here today, and I want to thank ITERA and ICPIAM for this opportunity to share my work with you. My name is Rifqy Maulana, and I'm from Engineering Physics Graduate Program. Currently, I work at PLN. Today, I will be presenting on DFT-based investigation of carbon dioxide reduction reaction activity and selectivity to CO and formic acid in nickel phosphate transition metal alloys. Currently, there is a continuous rise in atmospheric carbon dioxide levels. In response, carbon neutrality and green energy initiatives are gaining momentum, with carbon dioxide utilization emerging as a key approach. This process involves converting carbon dioxide into valuable chemicals or fuels like methanol, carbon monoxide, and ethanol through the carbon dioxide reduction reaction. Efficient carbon dioxide reduction to carbon monoxide has been realized by utilizing silver and derivatives of gold. At relatively low overpotential, CO2RR to CO and silver and gold electrodes can reach more than 80% in Faraday efficiency. The high performance, however, is undervalued by the high cost and relatively rare availability that will impede the wide application of the overall system. The selection of CO2RR catalyst for nickel phosphate because it's highly efficient electrocatalyst for the oxygen evolution reaction and the hydrogen evolution reactions. And this nickel single atom catalyst has been shown to enhance Faraday efficiency and suppress the HER. However, nickel-based catalysts still face the challenge of high overpotentials during the reduction process, which reduces their overall efficiency. Its potential as a catalyst for the carbon dioxide reduction reaction has yet to be explored. DFT calculations were performed using quantum espresso package. Ultrasoft pseudo-potentials were utilized to model the atomic core electrons with exchange correlation interactions approximated using the GGAPBE. Semi-empirical van der Waals correction were applied to account for dispersion forces. The surfaces of nickel phosphate and bimetallic nickel metal phosphates, referred to as NiPO and NiMPO, with the 100 facet were modeled as the active sites. In these models, the bulk structure was fixed, while the top layers were allowed to relax for interaction with the carbon dioxide. The 100 facet was chosen due to its availability as the most energetically favorable surfaces for both nickel phosphate and nickel metal phosphate. Energy cutoff was set at 50 RY for wave functions and 500 RY for charge density. And 15 Armstrong vacuum layer with dipole corrections were applied in the normal directions to prevent artificial periodic interactions. The system was relaxed until the forces on each atom were less than 0.0225 electron volt per Armstrong. For molecular calculations, a cubic cell of 30 Armstrong times 30 Armstrong times 30 Armstrong was used, with calculations conducted at the gamma point. It's evident that there's a slight difference in carbon dioxide absorption energy between the nickel phosphate 100 and the nickel metal phosphate 100 surfaces. Upon alloying nickel phosphate with transition metals, the carbon dioxide absorption energy marginally increases, typically ranging from minus 0.2 to minus 0.4 electron volt. For the nickel metal phosphate surfaces, the absorption energy was calculated at both nickel and transition metal sites. However, the difference in absorption energy between these two sites is minimal, suggesting that carbon dioxide can absorb equally well on both nickel and transition metal sites. As a result, the CO2RR process is likely to proceed at all available sites, regardless of whether the site is nickel or an alloyed transition metal. The reaction pathway results in the production of carbon monoxide from carbon dioxide involving two steps of electron and proton transfer on the catalyst surfaces. This pathway leads to the formation of formic acid, also through proton and electron transfers on the catalyst surfaces. This is also a two-electron reduction process, but the main product is formic acid. Both reactions involve carbon dioxide reduction by the addition of electrons and protons. The product depends on the intermediate formed on the catalyst surface. For COOH intermediate leads to CO production, and the HCOO intermediate leads to formic acid production. The catalyst surface, by the sign of star, where these intermediates absorb, plays a crucial role in determining the reaction pathway and product selectivity. For the carbon monoxide formation, the bimetallic nickel cobalt phosphate 100 and the nickel cobalt phosphate 100 surfaces, where carbon dioxide is absorbed at the nickel site, show a slight reduction in the free energy required to convert carbon dioxide to the formic acid compared to the pure nickel phosphate surface. For the formic acid formation, the nickel mangan phosphate and the nickel iron phosphate surfaces exhibit a more substantial decrease in free energy needed for the conversion of carbon dioxide to the HCOO, indicating improved catalytic efficiency over nickel phosphate 100. In this carbon dioxide formation pathway, the addition of binary alloys significantly reduces the limiting potential value of pure nickel phosphate when carbon dioxide is absorbed at the nickel site, especially in the case of this cobalt alloy. In contrast, for formic acid formation, the binary alloys lower the limiting potential value at both the nickel side and the transition metal alloy side. This indicates that transition metal alloys have a pronounced influence on the catalyst performance in both reaction pathways. It's essential to highlight that generally the C2OR process via this carbon monoxide pathway consistently exhibits a lower limiting potential value than the formic acid pathway across all surfaces examined. Thus, we can conclude that both pure nickel phosphate and its alloyed variants are in general more selective towards the carbon monoxide formation pathway, except for the nickel iron phosphate, which are more selective towards the formic acid pathway. The hydrogen evolution reaction is often considered a parasitic reaction because it competes with CO2RR for the same reactants, particularly the protons, the H plus, and the electron E minus, and consumes energy that could otherwise be used for CO2 reduction. Here are the key reasons why HER is seen as a parasitic process into RR. In our previous week, we observed that the transition metal site is not always the most stable for hydrogen atom absorption. Therefore, identifying the most stable absorption site for hydrogen is crucial before calculating the HER limiting potential on the nickel phosphate and the nickel metal phosphate surfaces. The absorption energies for various sites are summarized in the table. Based on the calculated values, the O-top site shows the strongest hydrogen absorption energy for both the nickel phosphate and the nickel metal phosphate surfaces, indicating that HER process will predominantly occur at these O sites. In the CO2RR process, the parasitic HER reaction is always present, leading to selectivity challenges. To evaluate selectivity, it's essential to compare the difference between the CO2RR and the HER limiting potential. A more positive delta limiting potential indicates greater selectivity for the formation of CO and formic acid, while more negative value favors HER. In the case of CO formation, some exhibit a relatively narrow potential difference compared to the HER, particularly at the nickel side of the nickel iron phosphate surfaces. For the formic acid production, the addition of transition metal alloys significantly lowers the limiting potential, but still fails to completely suppress the hydrogen evolution reaction. The best selectivity for the formic acid is observed at the iron side of the nickel iron phosphate system. Conclusions, the bimetallic nickel metal phosphate surfaces enhance the catalytic activity for the CO2RR and reduce the potential difference between CO2RR and HER compared to the pure nickel phosphate surface. This reduction in limiting potential difference increases the likelihood of CO2RR taking precedence over HER in certain alloy configurations. Based on activity and selectivity towards CO2RR, specific configurations show strong potential for this reaction due to their relatively small potential difference with HER. And number one is the nickel side of the nickel iron phosphate for the carbon monoxide, and the iron side of the nickel iron phosphate for the formic acid. Thank you for attention. Good afternoon.